Designing experiments while saving time and money. What a deal! Engineers and scientists love to test every possibility in running experiments. Today, we're going to talk about getting them the information they want and saving them time and money. When running a designed experiment, or DOE, one of the steps is choosing what factors to include in the experiment. Once you have identified which factors you're going to run, you must identify whether these variables are categorical, discrete, or continuous in nature. Today, we're only going to focus in on continuous variables. It gets a lot more complex when you have categorical variables in there. Now, when I say continuous, I'm talking about variables like time, temperature, pressure, concentration, length, and so on. There are three types of continuous variables that you might encounter. The first one is ratio data. An example is weight. 800 grams is twice as heavy as 400 grams. 12 feet is 3 times as long as 4 feet. That's where the name comes from. Ratio data works great as a continuous variable in designed experiments. Interval data. An example of this might be temperature in Fahrenheit or Celsius. 64 degrees is not twice as warm as 32 degrees. However, the interval between 64 to 65 degrees is the same as the interval between 32 degrees and 33 degrees. Interval data works great as a continuous variable in DOEs. Absolute data. Most often you see this as integer values, number of people, defects, particles, and so on. Count data definitely falls into this. Now, when we were studying statistics, we learned this as ordinal data, but it really goes beyond ordinal data. Ordinal data encompasses the world of cloudy, partly sunny, sunny. There is a definite order, but you can't quantify it. In this case, absolute data can be quantified, and 8 defects is twice as many as 4 defects. So even though those values are discrete, treat them as continuous. Absolute value works great in DOEs, absolute data, excuse me. Now, there was a famous statistician by the name of Stuart Hunter. He did great work in the field of designed experiments. He made a very astute and truthful observation. You spend 25% of your resources on your first experiment. Let that sink in. This is so critical. You spend only 25% of your resources on the first experiment. Designed experiments are never one and done. This mindset allows you to gain information and save money. So, now that we have that out of the way, before we go too much further, please like and subscribe down below. So let's start with one factor. Let's say it's temperature. You're going to run an experiment and vary the temperature from 100 degrees to 140 degrees. Now, this assumes temperature is linear. They come back with, we know it's not linear, Kevin. Let's run an experiment at 100, 110, 120, 130, and 140. 5 levels. Now that costs money and time, especially if there are other factors involved. Now the experiment got really complicated. If you are running the first experiment, you just need to know right now, is temperature significant? You're not trying to model it. If it is significant, you can start understanding that nonlinearity later. When you sit down with your engineers and scientists, they know it's not linear. They throw fits. Now, here's what you can do. you use center points as a part of the first experiment. You find the middle point of each of the factors. You'd still get some estimate of nonlinearity as well as if the factor is significant. So let's look at a real simple example. So we have a 2 by 2. So we have two factors at two levels, and that blue dot is a center point. And I've got some fancy names in here. If you care, great. If you don't, doesn't matter. But there's three types when we're trying to estimate nonlinearity as you could possibly run. And so you see this and you go, that's what I learned in design experiments. That is two factors at three levels, full factorial. All right, 3 to the 2. But there's some other ways that clever statisticians have come up with to get you information that works in your environment. And so again, we have the black dots. And if we were to add uh, tests to estimate nonlinearity, we could actually choose to do it this way. And there's a name for that. And then there's another way that we could do that. Again, the black dots are the two levels plus a center point. And if we need to add these red dots later, we can do that in a second experiment. And so there's a whole strategy. Now, when you're only running two factors, you probably said, Kevin, there's not a lot of difference. But here's where that changes when we have more than two factors. So in this case, you can see that cube down there. Those black dots represent two levels of each factor. There's a total of 8 combinations of those. And then we could add a center point. And that's what I would advocate that we do. But then you go, well, wait a minute. If there's nonlinearity, let's add in all that other stuff. Well, in this particular experiment, we could run 15 different experiments. If you had a 3 to the 3, that would be 27. And here's how it comes into play. If you have two factors, if you were to do it my way, it would take a total of 10 experiments. If you did a full factorial with only two factors, it'd only be 9. You're going, Kevin, nah, I think that other one's better. But if you have three factors in your experiment, my way would be 16 runs, and the way you were taught would be 27 runs. If you have four factors, my way is 26 runs, and the book way is 81 runs. So when I say the book way, when you get deep into design experiments, they say, do it the way I'm teaching you right now. Now, here's where you save time and money with your engineers. If the optimum, higher is better, lower is better, target, whatever that is a corner point, the impact is far greater. So let's look at that. We have a 2 to the 2 level. We're going back to two factors. If your center point is the best observation, higher is better, lower is better, optimal, whatever it is you're solving for, if that center point is best, then you would add those additional experiments, estimate the nonlinearity, and you're good to go. But if a corner point is the best, we employ a technique called the method of steepest descent. And if that is way over our heads, not a problem. But we issue out a projection from that experiment and we run some additional tests outside that box to say, okay, is there more opportunity outside that box? And it's called method of steepest descent. And let's say that third point that I put a little box was your best observation. And now you're going to build a new experiment around that value. And so now all of a sudden that upper left-hand corner is our best. So now we send out another projection. We do the same thing. We do it over and over until we have the optimal point in the center. And so in this case, We could then add these points, and technically they're called star points. And now we can estimate the nonlinearity as well as interactions and so on. Think about all the wasted energy you had mapping out that first designed experiment. Not worth it. So, hopefully that helped. You might have to watch this video a couple of times to fully appreciate everything, but it saves you a lot of money at the end of the day. So, bottom line, bottom line, with all continuous factors in your experiment, insist, almost mandate, that you only run 2 levels in your first experiment and add a center point. It will save your organization time and money. There is plenty of time later to map out the nonlinearity.